So the basic idea here is that I'm trying to, I have been trying to present some sort of view about what rational agents, how rational agents should think about the world with respect to how they reason about it, for example. So, sorry, yeah, that's right. So, and the idea here is that we want to be agents such that, for example, if we have a certain, we have a certain belief state, at time t. So, for example, we have a set of beliefs at time t, for example, right? So that's sort of my idea. And suppose we can represent roughly these beliefs that we have as just a number of propositions. So, so for example, right now, one of the beliefs that I have is that I'm talking to you. I'm teaching this lecture. That's one of my beliefs. So call it, for example, for example, let me be here the example. So I have the belief that I am teaching practical reasoning. It is Wednesday. The sun is out, and so on, right? So these are the sorts of beliefs that I have. There are other beliefs. So I'm pretty certain of these beliefs. I think that they are very likely to be true. So I will say that, for example, they are. If I'm thinking about them in terms of degrees of belief, which is something that I mentioned in the probability handout, and which is going to be basically the subject of this lecture that I'm talking about, the video lecture that will be up in the Moodle as well. So in terms of my degrees of belief, the sort of confidence that I have that these beliefs are true, well, I will say that they have, for example, this one has probability 1. It seems very likely to be true to me, roughly. And I have other beliefs, for example, right? So, for example, I have the belief right now that it's, for example, suppose you ask me, how likely do you think that there's life on other planets? So, for example, so I don't really know about that, but I think that there's, there's a non-zero chance that there's life in other planets. Probably more than that. There have been some speculations by scientists about that. So probably around 0.5. Another one will be, for example, that the material objects. So that's a pretty sophisticated belief, P5. But I do have that belief because, that's what general relativity says. General relativity says that, material objects reside in a curved spacetime. However, I am not certain of that belief because, science is always under revision. There might be some incompatibilities between general relativity and other fundamental theories. So let's say 0.6, right? So the point here is that I have this I could represent my beliefs at a certain time, a number of propositions at that time, and then think about many of them, I'm going to be certain. About many of them, I'm going to be certain that they aren't true. For example, I'm certain that it's false that I have a blue shirt. That it's false that I have a blue shirt at this time and I don't have a blue shirt at this time. So every contradiction is going to be false. I'm certain about that. And I can represent all of these beliefs as, as a number of propositions and give a sort of probability that they are true, right? And then the part of the claim, for example, involving probability and logic that I have been trying to motivate in the last lectures and with the handouts is the idea that suppose, so for example, how should I reason? How should I change my beliefs? If I learn new information. So let's just represent that new information by a proposition, call it Pn plus 1, Pn plus 2, and so on, right? So before I used to know propositions, or I had beliefs about propositions P1 to Pn, such as the ones that I explained here above. And then I'm asking the question, how should I change my beliefs at a later time, P2, if I learn new information, Pn plus 1, Pn plus 2, etc., right? So, and then my part of my suggestion is that I should change my beliefs by reasoning with that new information. Logic plus probability. So that's my claim here, right? So, and that's a necessity claim. So what do I mean? Why do I mean by that? I mean that part of what I'm saying here is that it is a necessary condition for rationality that when we update our beliefs from new information, we do so by appeal to logic plus probability. So that's part of what you need to do to be rational. That's my sort of my contention. I mean, I guess I will say perhaps maybe a belief which is a little bit weaker than this. Perhaps at some points you can add other information which is not already included in the information you can deduce or infer from that. So say something like this, right? So what do I mean by this claim? I mean, this is sort of looks like an obscure claim, but it's it's not really that difficult to explain what I mean by that. Part of what I mean is, for example, suppose that at time t, as I mentioned, I believe that I am teaching, I believe P1, I am teaching practical reasoning. And suppose I believe P2, which is like this. If I am teaching practical reasoning, then I am talking about rationality. So suppose that those are two beliefs that I have at time t. So quick question, what follows from those beliefs?
Would it be that you're talking about rationality?
Right. I mean, by what principle does it follow? Do you remember the name of the principle?
Is it one of the
Yeah, the inference rules.
it's either, is it modus, one of those?
Yeah, modus ponens, basically, right? That's the one that we use the most because that's
Yeah.
the most the typical. That's the one that people use the most in arguments, actually, in real life. So that means that if at time t I have this information, then at time t2, I should add p3. I am talking about rationality. That's sort of the idea that, for example, of what it means to update according to logic. So part of the idea is that if I have a number of beliefs that I'm representing by propositions at a time, and if then I should believe, then I should also believe whatever those propositions that I believe, whatever those propositions imply logically, whatever I can deduce logically from those propositions. And likewise, for example, for probability, suppose that I believe that, for example, suppose I have the following inductive belief, right? So suppose I believe at P1, so at time t, I believe that the sun is up. And I also believe this claim that something like that, then I should, in such a case, also add So, I mean, this is sort of like a rough sketch. I will need to be more precise to express the idea here, but by citing explicitly the rules of probability, the axioms of probability. But part of the idea is that if I acquire some new evidence, and if that evidence makes some propositions more likely. So for example, if I see that the sun is up, then that makes the hypothesis that it is warm more likely than if the sun isn't up, for example, right? Suppose that's the case. Then if I have new evidence that makes some hypothesis more likely, then I should update my beliefs to increase what I think is the probability of that hypothesis. So for example, suppose that before I saw that the sun was up, my belief that it was warm was 0.5. Then after I see that the sun is up, since the sun being up affects the probability that it is warm, then I should revise the hypothesis that it is warm. It will be more probable in that case, right? So inductive inference, right? So part of the idea is that I should revise my beliefs if I'm rational by using logic, by using probability. And then I mentioned this abduction, which I haven't talked about here. there's going to, I mean, there's like a brief discussion that I'm going to leave for you for the final about abduction, just like a brief question involving like a very short section of an article. But the very, very basic idea about abduction is, the basic idea here is that sometimes we form hypotheses about what's going on, which we cannot neither deduce logically by what we already believe, nor can we deduce from just pure probabilistic reasoning. And a lot of that has to do with the introduction of hypotheses. So just to give like a super quick example, suppose that I have, in logic, in deductive reasoning, if I have something like this, so for example, if I were just talking about deduction, this will be a valid argument because it has the same exact pattern as the argument that we discussed just as a moment ago. I have a conditional claim in one. If this, then that. In two, I have the antecedent of that conditional claim, so I can infer the consequent, right? So if P then Q, P, therefore Q. This is logically valid. If the premises are true, then the conclusion must be true. And this is a correct inference. However, if I were to say that the following thing will be a mistake, a logical mistake, deductive mistake. So from the information above, suppose that I have the floor gets wet. And then from here I deduce, therefore, it rained outside. So this will be fallacy. It will be a logically invalid argument. If you consider it from the deductive standpoint, just deductively, if you think about it just as a deduction, it will be invalid. It will be a fallacy. However, there's another way of thinking about it. You could think about it just not so much as a deduction. So you are not making the claim that if the floor gets wet, then it follows that it rained outside, but you make the much weaker claim that, the floor is wet. Maybe it rained outside. Maybe that explains. So something like this, the floor gets wet. So that supports the hypothesis that it rained outside. So this inference here, this second case, where we have, for example, we have some new information, the floor gets wet, and instead of, instead of deducing that it rained outside, which I cannot do because it would be a fallacy. So for example, if I have an argument of the form P implies Q, and then I have Q, from that it doesn't follow that P. I need to have P implies Q and P in order to infer Q, but from Q I cannot deduce P. Okay, that's a fallacy. It's not a valid rule. So taken as a deduction, it will be a fallacy. However, I could take it as a sort of different type of argument, and what is called an abductive argument, an abductive inference. And in that sense, it's just an argument that is meant to provide some support for some hypothesis. So I have this information that the floor is wet, then what could explain that? So that's the question that, for example, you should ask in science, or you should ask when trying to explain some empirical phenomena. You have some information and you see what will it, how will the world need to be in order for whatever I'm seeing or whatever information I'm getting to be the case, right? So if I have the information that the floor is wet, what's a good explanation of that? Maybe that it rained outside, right? I mean, another possible explanation might be that someone just threw, you know, like a bunch of people just threw water on the floor or something like that, for example, right? So then you should then consider more information, right? You should consider more information. So if I just see a lot of, you know, I go outside and I just see that the floor is, you know, wet everywhere, and there aren't that many people around, then that lets me rule out the hypothesis that it really was people, you know, throwing water on the floor. It really makes it far more likely that it rained. So, and that's part of the idea that, for example, the fact that the floor is wet is compatible with a number of hypotheses. Unlike what happens in deductive logic. In deductive logic, for example, if I have that if it rains outside, then the floor gets wet. If that's deductive logic, if that conditional is true, then if I have that it rains outside, then it must necessarily be the floor must be necessarily wet, right? So that, I mean, unless the conditional is false, right? So that's a possibility. Someone might object actually that conditional is false. There might be cases where that doesn't happen, but supposing that it's true. However, in abduction, some fact or some information is compatible with multiple hypotheses. So we still need to find out which of those hypotheses, all of which explain the data or the phenomena, which of those is the best. So that's sort of what abductive inference is, roughly. As I mentioned, there's like this excerpt that I'm going to ask you to read for the exam. It's on the Moodle already. But then part of the claim that I've been making, given all that I have told you right now, is that an agent or a rational agent, whenever they are updating their beliefs from one time to another, they should basically try to use these types of patterns of inference. They should either make the logical deductions from their beliefs to see what they, you know, what are the logical consequences of those. They should make probabilistic adjustments from their beliefs to see what those make more or less likely. And they should also generate new hypotheses from that explain some of the information that they are getting. So, for example, if I see that the floor is wet, that's a belief that I have that is based on empirical information. So I should try, if I'm rational, I should try to look for some hypothesis to figure out what explains that. I mean, obviously that doesn't, I mean, I'm not saying that every agent should spend all their time figuring out, you know, giving hypotheses for everything that they observe. No, that's not what I mean. What I mean is that either you are in the business of generating hypotheses. For example, if you're a natural scientist, or you're generating hypotheses perhaps in the humanities or somewhere else, but you're generating some hypotheses that explain some belief, or you might suspend judgment about stuff that you don't really know much about, or you're making updates in terms of logic plus probability. So that's sort of the claim that I'm making, right? And then part of the stuff that I've been saying up to now is that mathematics sometimes is very relevant for giving, for doing scientific representation. So what do I mean by that? I mean that roughly this very general idea, right? That part of what science does in fundamental domains is it gives maps about those domains. These maps allow us to make inferences about those domains. So so for example, think very briefly about the idea of a map, right? So what's a map of a city? For example, suppose you want to go to you're in a new city, you have just arrived to a new city and you want to go to your hotel, and then you are using Google Maps to find out how you can get there. Then part of what Google Maps is going to tell you is it's going to tell you your location, and it's going to tell you what are your surroundings, and it's going to give you a number of directions in order for you to get to where you're going. But the map of the stuff that you're going to be using in Google Maps is highly simplified. So it's not going to be like a 3D representation of the actual city. It's just going to be this 2D representation. For example, each block of the city is not going to be actually represented like accurately as like every color or every picture or every angle of every building. Obviously not. I mean, you have like this very 2D representation. Maybe you're going to represent a block of a city as just this gray square. Obviously, the distances of from one place to another are going to be changed in some way. But however, there are going to be certain similarities between the map of the city that you're seeing in Google Maps and the city in real life. So for example, it might be that you need to go 5 blocks to the right and then 1 to the left according to the map. So in the map, it's going to appear as if you need to go 5 blocks to the right and then 1 block to the left. In that pictorial representation of the city, even though it's like a very distorted. And when you are actually driving in the city, then you actually notice that, yes, you did have to go in the actual city 5 blocks to the right and then 1 block to the left, right? So the map and the city, are different in many ways. Detail, number of dimensions, and so on. However, they are similar in those respects that are useful to navigate the regions represented by the maps, right? So if they are similar in terms of distances, the types of distances you're going to be facing, directions, number of streets, etc., right? So there's this similarity. And then part of the claim that I want to make is that when scientists try to find out what's the nature of the world in many different domains, but I'm going to take a specific example, cases from physics, because these are in a sense, these are the most mathematical cases. So they are more strongly associated with the idea that I have been discussing. So part of what I'm saying is that when scientists, for example, physicists, start trying to think about the nature of reality, of space-time, of matter, and so on, part of what they do is they try to come up with maps of what reality is like. I mean, obviously, we cannot, as scientists or as human beings, represent a lot of information in our brains, or even, in a lot of detail about what space-time is like. We are very finite beings. However, we can give representations that are very similar, at least for those in the respects that we need those representations to understand whatever they are representing, for example, right? So, just as in the analogy of the city and the map. So, for example, think about time, just the nature of time. Let's not bring in I mean, we could do that because I have this is like a subject that I have written about relativity, but I mean, obviously that will like make this discussion very difficult. Let's just stick to the very intuitive notion of time. So notice that, for example, some interesting features about time are the following, right? So, for example, interesting features. So, if time if time t1 is earlier than time t2, and time t2 is earlier than time t3, then time t1 is earlier than time t3. That's one fact that we notice about our experience of time. That's right. I mean, that it's ordered in this way. So, for example, last week, Monday was before Tuesday, and Tuesday was before Wednesday. So Monday was before Wednesday, right? So that's like a typical experience of time. That means that, for example, this relation time happens to have this property that the relation earlier than is transitive. So that's one important property right there. An important property that I can actually give like a sort of mathematical representation of. I know what it is like mathematically for there to be a transitive relation. I know exactly the meaning of that. So here's another interesting feature about time. So for example, between any two times, Tm and Tn, there is a third time, call it Ts. So part of the idea is that, for example, if I think about the nature of time, it doesn't proceed in a discrete manner. So it's not as if there's a second, then there's another, like there's nothing in between, and there's another second, and there's nothing in between. No, there's, for any two times that I choose, I can always imagine a third one between those two, right? Actually, this also applies, and for example, this is sort of property that is called density. Time is dense. And so those are just some of the properties of time, right? And I can actually, space has some of the same properties. So for example, between this point A and another point B, which is a certain distance from A, there's always going to be a third point between those two. So space is going to be dense as well. And for example, if point 1 is to the left of point 2, and point 2 is to the left of point 3, then point 1 is going to be to the left of point 3. So the relation to the left of is also going to be transitive, and so on. So all of those relations, as I have explained, for example, in the discussion on relations and functions, all of those relations have logic. Those are logical properties of relations. That whether a relation is transitive or not transitive, symmetrical or non-symmetrical, those are logical properties of relations. We understand their behavior pretty well logically. So, for example, this is like a very, very simple representation of time. Just I can represent time just as a line. And we can see, for example, that in the line, for example, if this is T1, and this is T2, and this is T3, I just chose like three arbitrary times, right? But I can see that these satisfy this requirement here. Like for any times they are the relation earlier than is transitive. I can also find always another time between any two times, here and here. So the real line is like a very simple representation of time. It's a representation that some of the earliest physicists, for example, Newton, when he was thinking about time, Newtonian time, that's basically what it looks like. It's like the real line. It has the same mathematical properties as the real line. So part of the idea here is that we are not saying obviously that time is exactly like the real line, that so exactly like this line. No, part of what we are saying is like this line shares some similarities with time, as represented by Isaac Newton, for example, and the classical physicists. Similarities such as these ones here. That's part of the claim. So part of what it means to find, for example, part of what it means to use mathematics to do scientific representation in physics is to find pieces of mathematics, you know, the real numbers, natural numbers, and so on, geometry, etc., that bear certain structural similarities to whatever physical phenomena we're trying to represent. So that's why I mentioned, I mean, part of the discussion, for example, in the two papers that I mentioned that you should read if you have some time, in the Russell paper and the paper by Colivan and Bueno, the first sections. Part of the idea that there is that when we are, for example, when physicists start looking at the world, part of what they see is they notice certain patterns, for example, right? They might notice some patterns about how space is, you know, what are the relations between the spatial objects? How are they, you know, what happens if A is situated here and B is situated there and C is situated there? What can we see about space or about time, for example, right? And then they notice certain patterns, they notice certain logical relationships about material objects have in time or in space. When they, I mean, that's going to be something that they notice in the empirical domain. They are going to notice certain patterns and relations. And then part of what they do is they go to the mathematical domain. And here we have a number of, you know, of theories that we can use. We have geometry, we have the natural numbers, the real numbers, and so on, complex numbers. And all of those numbers can be described. I mean, obviously, I mean, there's a lot of detail going on there, but all of those can be described by the sort of axioms that we discussed when we were talking about the Peano axioms or the Kolmogorov axioms in probability, or the logical principles of inference. All of those, you know, like you can give a number of finite rules or finite principles that actually describes logically what geometry is like, or what the natural numbers are like, or what the real numbers are like. And then you can, you know, the scientist then detects these patterns and relations, goes to the mathematical domain, looks for the sort of, you know, whatever mathematical structure might be useful to represent those phenomena. Looks, you know, scientist looks for useful mathematical structures that has similarities to those physical phenomena. And if they find a good, you know, a good mathematical structure to represent those phenomena with, then they can use that mathematical structure to actually start making inferences about what the world is like, and deductions and probabilistic judgments and the like. So, you know, they come here, they do this, and then they go back here, and finally they can use those mathematics maps to make deductions, probabilistic judgments in the relevant empirical domain. And sometimes, for example, the Newton story is actually an illustrative case, because Newton started out having some basic ideas of what the geometry of space was like, the geometry of the, you know, the nature of time was like. He used some basic mathematical structures to represent those. He was very successful in representing those and then using those maps, those mathematical maps, to make inferences about the physical world. And eventually, you know, they found out that it didn't really cover all of the stuff that, I mean, there was some stuff about matter or about space that the Newtonian theory couldn't cover. So they had some new information, and with that new information, they made updates, and they were able to look for better maps, better mathematical maps. That's how relativity came about and quantum mechanics. So that's obviously like a very sketchy idea. Not enough time to go over all those details. So let me just briefly, before we end the class, just give you like a more precise definition of what's going on here. So there's this mathematical relation called isomorphism. So remember, we use sets to group things, so we can use sets to represent whatever we want. So we could talk about the physical world and think about it as a collection of things, as a set of things. And we can also think about mathematical structures or mathematical objects as sets. So there's going to be an isomorphism between sets A and B if and only if there is a bijective function f between A and B. So it's 1-to-1. It goes from every element of A to one element of B and only one element of B. And every element of B is covered. So, so for example, something like just to give an example, something like this. This is a bijection. So that's sort of the idea. I mean, what am I saying here? Just to express it more clearly, if you have, there's going to be an isomorphism if you have two sets A and B. There's a bijection between them, so a function that does something like this. It goes from one to the other, and it exhausts everything here, and it's just 1-to-1. And if you have objects that have some relation in the domain, some specific relation are in the domain, so such as, for example, being transitive, so like A being earlier than B, then for example, in time, then they are going to be the points in the real line are going to be one before the other, right? So there's going to be like a similar relation in the map as in the representation. Whenever the objects are related in that way in the world, they are also going to be related in that way in the map, right? These relations are, the specific name of these are isomorphisms. But then the idea, just to finish this lecture, is the idea is going to be that when you're trying to make abductions about the nature of the world and trying to use mathematics to make those abductions and find out what's the nature of those, those parts of the world, then mathematics is useful because it can give you a ton of useful representations, which are very simple. And you can use those parts of mathematics to reason about the world, just as long as you can find similarities between the world and those parts of mathematics. So even if many of you are not scientists or physicists or whatever, it's important that many of you at least understand why the physicists make, for example, such bold claims as they usually make in the news. Because part of what they are doing is they have this data or all of these observations about the physical world, and then they make inferences about what sort of mathematical structure is actually representing that. And then they can make, because in mathematics we actually know a lot, they can do a lot of inferences then that if the world is actually like the mathematics, then it must have such and such properties, right? So So yeah, that was basically the idea. And then you know, the stuff about that Russell was saying about the importance of mathematics with regards to the Zeno's paradoxes and the like. Part of the idea there was that until we had this notion of representing through mathematics, space and representing spaces and time through the proper mathematics, we couldn't really know what was going on. And that was like the really great leap forward that happened in the 19th century. We had the proper logical tools to do that. So yeah, that's basically what I wanted to discuss for the last synchronous class. But again, there's going to be like another lecture on the probability stuff just to round that up. So yeah, are there any like last questions or anything else that you want to ask before we close this? Well, thanks a lot for coming. And you know, if you need to, obviously I'm going to be available by email, you know, for questions about the paper, for questions about the exam. As I mentioned, the exam is going to be up on May 8th. And yeah, I encourage you to email me for anything related to that. And I'll also be in touch for stuff having to do with your grades in case I'm missing something. So you should be checking your emails a lot also for that reason. Thank you.
Thank you. Have a good day.
Thank you. Have a good day.